right, next I'd like to look at the rotating black hole solution to Einstein's field equations, and that is a solution that was not immediately evident when Einstein first discovered his general theory of relativity back in 1915. The non-rotating black hole was a relatively easy problem to solve and was solved by Carl Schwarzschild about 2 years after Einstein had first discovered his theory of general relativity. But the rotating black hole solution is perhaps a more physical solution because the star originally is rotating. And so as the star collapses under the influence of gravity, we would expect that its spin rate would pick up. And so because of that, it took all the way until the 1960s to discover the rotating black hole solution once computers could help to solve the problem. And so this is kind of an interesting variation on black holes. Instead of a point singularity, we have a ring singularity. And so this is a one-dimensional ring looped back around on itself with a void in between. Surrounding the ring singularity, you have not one event horizon, but two. Here's your inner event horizon. And then surrounding that, we have the outer event horizon. So this would be the rotational axis of the black hole. This would be the outer event horizon. So as if one event horizon weren't enough, now we have two. And so the idea then is in this region between the inner event horizon and the outer event horizon, literally space and time is being dragged along with the black hole. This is called the ergo region. And it's impossible to stay motionless in this ergo region. You have to be essentially carried along with the space and time that's being dragged around the black hole by the rotation. And so this is sometimes called frame dragging and has been conclusively demonstrated in less exotic situations with rapidly rotating stars, that there is some space-time dragging that's taking place. And so if you solve these equations for the rotating black hole, you end up with something that is kind of surprising. You can, let's say for example that you have a universe that is three-dimensional instead of two-dimensional. So here I'm going to suppress the dimensions by one. But let's say that you could bend that space back around on itself. Then, according to Einstein's field equations, there might be a way that you could fly through the ring of the singularity of this black hole and come out somewhere else in the universe. So in other words, these 2 points would seem to be greatly separated in distance if you were to just fly there the long way. But if in some sense there was a shortcut because of the extreme curvature of space, you could perhaps just pop right through, take this shortcut route, and end up anywhere else in the universe that you wanted. And another possibility is that there are other universes. And so these black hole solutions could also open you up to the possibility of being able to travel into a completely different set of space-time dimensions. And so this has been quite a booster shot to different kinds of science fiction stories that have been written over the years, where you fly through a rotating black hole and end up in another universe. And although these solutions do allow for this kind of travel, there are some problems with traveling to other places through the rotating black hole solution. One of these problems is that now we have two event horizons rather than one. And as we learned last time, each time you cross an event horizon, an infinite amount of time goes by relative to the universe you left behind. So somehow these infinities would have to cancel out. And so that's one problem. Infinite time passes each time you cross an event horizon. Just a minor problem. The second problem is that you have these what are called tidal forces that would stretch you. So as you fall toward the ring singularity, the force of gravity on your feet becomes much larger than the force of gravity on your head, and you'd be stretched apart. And we mentioned that as a difficulty earlier, but that would be still a problem here. So the tidal forces would pull you apart. This is just like the kind of tidal forces that act, say, with the Earth on the moon to stretch the moon. Okay? But here, the tidal forces would be much more extreme. And they'd pull you apart multiple times. A third problem with the rotating black hole solution is that as you, and let's say here that you're actually flying through the ring singularity. This is what would bring you, according to the field equation solutions, through possibly into another universe. Is to fly through that ring, and then in this curved space, you could presumably end up somewhere else in our own universe. Remember, this is a coordinate in space and time, so it could be another time as well as another place. Or you could end up possibly even in another universe. But we have a third problem with this, and that is that there should be quantum radiation given off by the ring singularity. So this is one of those situations where I would definitely want to see somebody else try it first before I did it myself. And so this actually kind of puts a damper on some of these science fiction movies in which you fly through a rotating black hole and end up in a new universe. And so Carl Sagan in particular was a person who wanted a more realistic kind of a scenario for the book that he was writing. So he went to Kip Thorne, who recently got a Nobel Prize for helping to co-discover gravitational waves with the LIGO experiment. And so Kip Thorne, being a friend of Carl's, worked through the idea, and if we could just look up here at the data projector for a second. Here is our rotating black hole solution. Again, the ring singularity, the ergo region, the inner and outer event horizons. Interesting, but maybe not so conducive to making that jump from one place in the universe to another. What seems perhaps to work better is to use a wormhole. And so this is what Kip Thorne worked on to help Carl Sagan with this story. And the idea then with a wormhole is that you still have this way of bridging that gap between different regions of the universe, different regions of space and time. But in the process of doing this, you have this shortcut route through the wormhole throat, or you have this long way around. And so this long way around then could take you, say, 1 billion years to go this way. But going this way, you might only have to travel the distance of a football field, or even less. And you could end up in some other place, space and time, in our universe. Okay, so the idea then with this is that, again, you need some kind of a curved space. And then you would bridge that gap. Now, how would you make this wormhole? Well, we're not really sure. Some people think that we might be able to take a microscopic wormhole, which are just randomly being generated all the time, according to some ideas in quantum physics, and just magnify it to macroscopic dimensions. Another possibility might be to take, say, a whole bunch of white dwarf stars and get them swirling around and round in a circle and essentially create a cosmic vortex that might possibly work as a wormhole. But this would be the wormhole mouth. This would be the wormhole throat. So this might be, say, us here on the Earth. And now here, this could be, say, on this side, the Vega star system. So this would be perhaps a huge benefit to anyone who wants to explore the universe. Because if we're, say, going to try to go even to the most nearby star, Alpha Centauri, if we go fast enough to actually make the trip, the time intervals will be so huge by the time that we get back. The Earth might have aged through 1,000 years in the amount of time that it would take us to get there and back. And so this way, you could go back and forth in real time and explore different parts of the universe. Just our galaxy alone, if we could explore a lot of that, that would be amazing. But remember, we think, as many as 2 trillion galaxies in the visible universe, and the universe as a whole may be much bigger than that. As a matter of fact, there could be other universes. So being able to explore the rest of the universe is really out of our reach unless we have some kind of a mechanism for doing this. And this is what the wormhole allows for. Okay? And so this is a possible alternative then to the rotating black hole for trips to other parts of the universe. So what exactly is this wormhole? Well, it is a highly curved region of space and time, but with no singularity and no event horizon. So if you'll recall, the main problems with the black hole solution were that you had quantum radiation being given off by the singularity, and you had two event horizons to go through, each one of which would result in an infinite amount of time going by. But if you could have this highly curved region of space and time that avoid the problems that are involved with infinite time stretch, and you could also eliminate the quantum radiation, then the only other problem with the with the black hole solution was the tidal stretching. And so you could adjust the curvature of space and time so that you wouldn't be stretched too much. You know, maybe just 1g gravity acceleration wouldn't be enough to create any noticeable discomfort. You might feel just a slight pulling apart, but it may be like a chiropractic stretch. So this then would solve those black hole problems, and so Contact was the name of the book that Carl Sagan wrote, and eventually was turned into a movie. I don't know if you've seen it or not, with Jodie Foster, but they discovered an ancient web of wormholes that were connecting different parts of the universe together, and it was self-maintaining. The civilization had long since died out, but they were able to take these trips because of the existence of this wormhole system that had been developed by an arbitrarily advanced technology. There are, however, some problems with the wormhole solution too. So we don't want to necessarily think that this is all just going to be easy or even possible. We're not sure yet. One problem with the wormhole solution is that you're not just going to find a wormhole sitting out there in space. According to our best indications of what's going on, wormholes are unstable. And so what you would need then is some kind of an arbitrarily advanced technology, maybe with space stations that could thread matter and energy through the wormhole throat in order to maintain the stability of the wormhole. Because just the act of a rocket ship flying through could cause the wormhole to pinch off. And that means that your space and time would just be ripped to shreds if you tried to fly through without some kind of stability. Now, how do you make this thing stable? Well, you could thread electromagnetic fields through it, because energy can also bend space, not just mass, but also energy can do that. So with electromagnetic fields, you might be able to bend the space in just the right amount to compensate for any instabilities that are created by the rocket ship flying through the wormhole throat. So this is what we believe is needed then. We need an advanced technology to stabilize the wormhole. How soon would we be able to do this? No time soon. But maybe in the future, maybe 1,000 years in the future, or, you know, we've underestimated our ability in the past. Maybe just a few hundred years would be all we needed. Another problem is that you need negative energy in the center of the throat. So what this means then, negative energy, is like antimatter, not antimatter, but anti-gravity. You need negative matter. And the amount that you would need might be, say, the mass of Jupiter. but anti-gravity mass. Okay, so I'm not talking about antimatter like protons and antiprotons, because that has positive matter. That still attracts with gravity. What I'm talking about is some kind of if you had negative matter, you put it on your backpack, you would repel away from the Earth. You wouldn't be attracted to the Earth because it would generate anti-gravity. Okay, and so we do know that there are places in the universe where negative matter exists. And interestingly enough, one of them is just outside the event horizon of a black hole. However, we don't know yet whether there is some limit as to how much of this negative matter could be produced. The laws of physics have not yet been fully explored in this area. So this is a big question mark, whether we could put enough negative matter together to keep the throat of the wormhole stable. Okay? And so just to give you an idea of why we would need an advanced technology to do this, let's just imagine for a moment an analogous kind of an unstable system. Here, we'll put a bowling ball on the head of a pin. Okay, now theoretically, you might be able to balance that bowling ball on the head of a pin. But the slightest instability, even somebody opening the door, a little bit of vibration, or a slight wind current from the air conditioner turning on would be enough to cause that bowling ball to destabilize and start tipping in one direction or another. And so you would have to have some kind of a complex feedback mechanism here that could, as the bowling ball is detected to start tipping, to push it back to its original position. And so you would need an analogous kind of a thing with the wormhole mouth and throat. And that's what that advanced technology would do, is it would just keep adjusting the curvature of the space in a similar way to the way that this bowling ball could be adjusted to maintain its stability, even though it's in a position of what we call unstable equilibrium. So this is a possibility then for the future. And even if wormholes don't work, this could be a starting point for understanding other ways that we might be able to explore the universe.